We had three of them that need to be aware of: the temporary dipole, the permanent dipole, and the unusually strong dipole. In other words, the induced dipole, or the London dispersion, the dipole force, and the hydrogen bond interaction. These are the three big ones, and those are very important. Those are very important because they're going to have an impact on properties. So if we look at liquid properties, they're going to have an impact on pressure. We call vapor pressure. Vapor pressure, they're going to have an impact on other properties as well. So the vapor pressure, you know, depends on how easily the molecules vaporize, and you know, if they're weak forces holding the molecules together, they'll vaporize quite easily versus strong forces. And so vapor pressure is just one. What were some of the other properties of liquids that intermolecular forces have an impact on? Can you name them, or not really? And some other ones would be just in order of presentation. Evaporation would be related. You know, things that evaporate quite easily are called volatile. Although, you know, volatility didn't come into play. Evaporation, as well as condensation, depends on how well we stick together. But we had heat of vaporization, boiling point, viscosity, surface tension. Those were pretty much the properties that are going to be impacted by intermolecular forces. So intermolecular forces are important for those. And so this just went into talking about those, you know, the dynamic equilibrium, boiling, these, just the properties. All right, then we had a couple of other topics. One topic was gas mixtures, you know, whether we use Dalton's visualization or Avogadro's. Mixture is this exact same, just two ways of visualizing it, Dalton's or Avogadro's. Then we had the solids. You know, solids, we had crystalline and amorphous solids. Then there are different bonds that hold them together. So that was pretty much chapter 15. Oh yeah, and the energy calculations. These energy calculations, we had two. We had change of state or phase change, or process, you know, where heat of the process is delta H of that process times amount. And then we had objects, we saw over here. Here. Where the heat transferred in an object goes into warming it or cooling it. So it's the amount of object times the specific heat times the change in temperature. So we had heat related to processes and heat related to objects. Processes like vaporization, condensation, fusion, freezing. And then we had this curve. And so that was it for chapter 15. And then we're going to move on to chapter 16 next. So this is the last slide we did, was heating and cooling curve. Chapter 16 deals with solutions. So what happens when we take something and dissolve it into a liquid, we form a solution. So this is looking at liquid solutions here. So these are the learning objectives here. Let me just skip through those. Solutions are homogeneous mixtures. They don't have to be liquid solutions. We could have gas solutions and solid solutions. Gas solutions would be like air. You know, they just look homogeneous, they're uniform. Solid solutions would be like alloys, like sterling silver. Sterling silver would be a solid solution. When we're dealing with solutions, the minor components we usually call the solute, the major component we call the solvent. We dissolve the solute into the solvent, typically. Here's a solution here where we've taken copper-2 sulfate. Copper-2 sulfate is crystalline or amorphous solid. Tell by looking at the structure. This would be crystalline. Now you can tell it's very well ordered. It's well ordered, but it's crystalline. You got a crystalline solid. Sulfates, copper 2. This is not copper 2 sulfate. Sorry, this is copper 2 chloride. Just looking at it. Looking at this, it looks like copper 2 sulfate, but this is copper 2 chloride. Is copper 2 chloride soluble in water? Yes, you can dissolve it in water. Soluble salt's a strong electrolyte, so it's going to split up into copper 2 ions, which are the small gray ones, and chloride, these big orange ones. So we've got copper 2 ions and chloride ions. What happens when it dissolves in water is it gets surrounded by water molecules. And this is called a hydration sphere or a solvation sphere. And so basically, like a layer of water molecules surrounds this, forming a sphere. And if you look at the water molecules, the oxygens are all pointed to this. And that's to maximize electrical interactions there, because the oxygens are going to be negatively charged. They get the delta minus. And then we have a positive charge here, so that's going to be a favorable electrical attraction. So these are held together by Coulombic attractions. But this type of attraction is not terribly strong. So a water molecule can come over here and knock this one off and exchange itself for it. And so these hydration, but they help stabilize the solution. So here we have chloride ions that have been hydrated, that is surrounded by water molecules. But in the case for the chloride, you look, the opposite ends are attracted. So we see the hydrogens being pointed towards there. Again, we'll all have a hydration sphere, and this hydration sphere will help stabilize it. Typically, let's see, 1, 2, 3, 4, 5. There are 5 water molecules, but we probably can fit more than that. Sometimes 6, 6 is a common number. Like for the chlorides there, it's like, 4 in the plane, 1 on top, 1 underneath, 6. So that's what's helped stabilize it. Okay, if we can dissolve a lot of stuff in there, we can make a fairly concentrated solution. So concentrated means a lot of solute. Dilute means very little solute dissolved in there. This is kind of a tricky slide, because what are they trying to get across here? What they're trying to get across is this is a dilute solution. You can see by its light blue color. Copper 2 in water forms a blue color. And so we don't have that many copper 2 ions in here. It's light blue. If we get a lot more, it's dark blue here. See a lot more. Where did the copper 2 ions come from? The copper 2 ions, in this case, came from a reaction. Copper wire with silver nitrate. So let's see what that reaction is here. If we do copper and silver nitrate, what's the formula for copper? Cu. Solid, liquid, or gas, or AQ. It's solid. Copper wire plus silver nitrate. Formula for silver nitrate is just given there, AgN of 3. Are we okay to use, what form does this look like? This looks like an A plus BX. You see that? A plus BX? So it looks like a single replacement, but we have to be concerned, because there are exceptions with the single replacement A plus BX form. What are the exceptions, the common exceptions here, where we wouldn't want to use the single replacement method? In single replacement, A should be the reducer or the oxidizer. What should A be? A should be the reducer. So A should be the reducer. What other reducers do we have? The exceptions, I'll tell you, all the exceptions are based on this not assigning incorrect roles. When we put it into single replacement here, A is supposed to be the reducer, B is supposed to be the oxidizer, and X is supposed to be the spectator. And all the exceptions are when their assigned roles aren't really their preferred roles here. And so we could see that when when we think, okay, what other reducers are present? And so what we do is we'll just take a quick look here. The most powerful reducer is lithium. This is a bit odd. Let me just take a side journey here and talk about lithium. As far as lithium is a very small atom. A small atom is harder or easier to ionize than a large atom. Potassium is a lot bigger than lithium, a lot bigger than lithium. So let's say potassium is this big, lithium is like this big. And so which one is easier to take the electron off? A potassium, big potassium, or a small lithium? Potassium is a lot easier to remove the electron from. So potassium is a lot easier to remove the electron, then it should be a better reducer because reducers are electron rich. And the easier it is to take the electrons, the better it should be. And so I would predict potassium to be a much better reducing agent than lithium. And we can also see that because there's an energy that we associate with taking an electron off an atom. Do you recall the name of that energy? What is the energy called? The energy to remove an electron off an atom is called the ionization energy. And so when we compare the ionization, potassium is indeed easier to ionize than lithium. If it's easier to ionize, then an oxidizer is going to have an easier time plugging off the electron. And it's true. The oxidizer does have an easier time plugging the electron off potassium. And what results is potassium reacts much more violently with water than lithium does. In fact, let's just take a quick look at this because I'm sure this. Let's just look at the comparing the difference between K with water. Okay, that's a reaction with potassium and water.
Welcome back to an edition of Wikipedia Experiment.
Wikipedia. Hopefully you wear goggles, otherwise I can't show this.
See what happens. I'll wipe that right there. See what happens. Wait. It was red.
Okay, let's see this. Let me fast forward here.
Alright, great, right there.
Alright, so if you got a big piece of potassium, it's pretty violent. Let's see if we get a bigger.
It tends to just sit on the top and kind of bounce around. You really need a lot of water, right? So now and then it kind of explodes. So I created this. So this is a bag with two lead weights. Those are for fishing. I'm gonna go ahead and stick the rest of the potassium solid state right in there. I'm just gonna throw it on in there.
Okay, let's fast forward a little bit. So that's potassium. You can see it's pretty violent, the reaction.
When you submerge the potassium in the water, it definitely...
Let's look at the reaction of lithium and water. Maybe we'll try this one.
We have low ionization. One of the ways that indicates that high reactivity is to prevent or limit the reaction.
Okay, so this is in mineral oil to protect it from water.
Physical properties for group 1.
Okay, let's off the audio here. So that's a lithium stick. You can see there's a lot less corrosion on the lithium than there was on the potassium. There's a lot more corrosion on the potassium. There's some fresh lithium. Fresh potassium looks the same. Has a really shiny silver luster to it. This is just a conductivity, so it conducts electricity quite well, as do metals. But look at the difference in reactivity versus potassium. You know. This reaction is a lot less violent than potassium's reaction. In fact, usually no flames, you know, hydrogen gas is being generated, so in this case, it's not getting hot enough to ignite the hydrogen, whereas potassium, it easily gets hot enough to ignite the hydrogen. Here they're capturing the hydrogen, looks like. So they're going to test it with the candles and hydrogen. We'll form a little pop here. You guys did this in the lab too. A little pop with hydrogen. This is a test. It's also turning the water quite basic. It's shown failing. But the point is the reaction. I mean, potassium for sure is a lot more violent. And so why is lithium at the top? Well, you can think of the reaction as occurring as two stages in a way. The initial reaction, which potassium is a heck of a lot more violent. And then what happens at the end, you know, the end is kind of this little slow release of energy. The slow release of energy happens when we form the product. When we form the hydrated potassium ions, some energy is released because we're forming the, this is called an ion dipole attraction. So it's forming an intermolecular force of attraction in there. Whereas lithium forms a much more stable product. It just isn't, you know, the heat is released a lot slower. And so when we look at the hydrated ions, a hydrated lithium ion versus a hydrated potassium ion is going to be a heck of a lot more stable. And so the positive charge here is going to be a lot more concentrated in lithium. And therefore, there will be a stronger, what we call ion, the positive and the dipole. So this attraction is going to be a lot stronger. Whereas the positive charge here is a lot less concentrated. And so this attraction is going to be a lot weaker here. And so it's due to the formation of these very strong hydrated, very stable hydrated ions. That's why this one. For sure, this reacts a lot more violently. Cesium would be even more violent than potassium. Cesium would be here, but cesium, as far as hydrated ions go, you know, the ions is kind of big. You know, the positive charge is spread out. And so the reason lithium is at the king or the queen here is at the top is because of these here, the hydrated ions. So that's, you know, even though not much is talked about, this. Here, these hydrated ions are pretty important. This explains why, or at least describes why lithium ions are lithium's at the top, you know, reducing this hydration spheres. But anyway, let's go back to this here. So we don't have lithium in this particular reaction. So what reducers do we have? Well, we have copper. What other reducers do we have? Are silver ions reducers? Are silver ions reducers? No, silver ions are oxidizers. Silver ions are good oxidizers. Silver metal is a reducer, but we don't have silver metal. We have silver ions. Nitrate. Nitrate a good reducer? No, nitrate's on the oxidizer side too. And the only other thing we have is, well, we got copper, yeah. And what else? One more thing. Water. And so what's a better reducer? A metal like copper or water? Well, You might think water, but actually the metals are good reducers, like lithium. Even copper, although copper is not very reactive. Copper is a coinage metal. It's still way better than water. Water is way up here. And so copper is way better. So this so far is good. I don't expect this to be an exception. Versus, what if I had this? You know, what if A instead were chlorine? Does that make sense? You know, in single replacement, A is supposed to be the reducer, but if A were chlorine, what would you think? Chlorine, is that a good reducer? Is chlorine a good reducer? No, chlorine's not a reducer. Chlorine is an oxidizer, so something's definitely wrong. But copper, no problem. No, copper can be a reducer. Copper's a metal, it's a reducer. It's not a great reducer, but it's a reducer, and it's going to be better than water. Now we have the issue of oxidizer. So silver ions, yeah, you know what? Silver ions are good oxidizers. You know, this is why you don't want to touch this stuff. You don't want to touch things that contain silver ions because they'll oxidize it and precipitate out black little crystals of silver metal. So silver ion is a good oxidizer. Okay. And so it looks like single replacement's good so far, except for X. What is X? Spectator. And so is nitrate really going to be a spectator? No, in fact, when you look at the chart here, nitrate is a stronger oxidizer than silver ion, so this is primed to be an exception. We would expect this nitrate not to be a spectator. Nitrate's more powerful than silver ion, so nitrate's going to go in. Except for something. Nitrate's missing something. What is nitrate missing? Yeah, there's no H plus here. So I think I mentioned this before. This is like, you know, if a key ingredient's missing like H plus here, it's not going to work. We just need some source of H plus. And so one way to fix this is to add some acid. If I add some acid to this, let's say plus HCl or something like that, then no problem. You know, HCl is going to give H plus. But since we don't have any acid in there, then it's not going to work, and its ranking is going to go way down because we need the H plus to form water. And if you can't form water, it's not going to be as favorable because, you know, the more stable product you can make, the better. It's the reason why lithium is so powerful. Lithium is so powerful because not because of its reactivity, it's because of the stability of the product it forms. And so here, without the H pluses, no water, which means that the ranking is going to go way down. And so in Chem 1B, you could figure these things out. In Chem 4 and Chem 1A, we don't. We're just going to say that, okay, we're missing this, therefore we're not going to make that. Therefore, we're not going to consider it. And so nitrate's missing H plus. And so this is okay. Since it's missing H plus, then silver ion will be the strongest oxidizer. Present copper is the strongest reducer, and this should work. This should work to form what? Copper nitrate. What's the formula for copper nitrate? Is it copper 1 or copper 2? When you look at the redox chart, copper goes to copper 1 or copper 2? Copper 2, so it's going to go to copper 2. And so the formula here should be Cu. That's correct. And then the other product is going to be what? The other product is going to be silver. Okay. Before we balance this, what is the driving force? Silver is, what is that? Solid, liquid, gas, or AQ? Does it form silver plus or silver? Silver plus or silver? It forms silver, which has a solid state. And so I know what the driving force is. The driving force is precipitation. Is that right? No, because precipitation only works for what type of reaction? Metathesis. This is not a metathesis. This is a, what type of reaction is this? I don't want single replacement. I want, what kind of reactions are single replacement? Are they metathesis, redox, or acid-base? Single replacement, redox, metathesis, or acid-base? Acid-base? Well, one way you could tell is if there's an oxidation state change, if the charges change. What's the charge on silver over here? Plus. The charge on silver over here? 0. And if there's any change in charge, it's redox. Because acid-base and metathesis have no change in charge. All the charges stay the same. That is the charge on individual atoms. We'd look at the oxidation states on those. And so this is a redox reaction. And for redox, what's the driving force? What do we look for in driving force? Well, if we do the single replacement, we could use activity series. Going from more active to less active is the driving force. So copper, is that more active or less active? What's the most active? Lithium is the most active. It's not the most reactive. The most reactive here would be potassium on this list. Here's copper up here, and we're comparing that to silver. Looks like copper is more active. And this is less active. So this is what we call our driving force, going from more active to less active. This is for single replacement. If I were doing this as a regular redox, then I'd say that this is a stronger reducing agent, this is a weaker reducing agent. And likewise, that means silver ion is a stronger oxidizing agent, and copper 2 ions are weaker oxidizing agent. And nitrate is a spectator. So if I compare the ions, silver ions are stronger, they're closer to fluorine than copper 2. But we just need one, the other would follow. This is why they only look at the reducing activity, not the oxidizing activity. Because we could have oxidizing activity, this would be the more active oxidizer, that would be the less active oxidizer. All right, so we have driving force. Let's go ahead and balance it. We'll need 2 silver nitrates, and then we're going to form 2 silver metals here. This would be the complete equation. For when you do single replacement, I want to see the complete equation, the ionic equation, and the net ionic equation for it. If you do chart method, then only the net ionic equation is what we're going to get from it. We could get the others, but it's a bit more work, and it's not necessary. And so let's go ahead and get the ionic equation. Copper, do we ionize that? Or just leave it alone? Do we ionize it to copper 2? If I put copper 2 down here, that's totally wrong, because all 3 equations, the ionic, the complete, and the net ionic, are supposed to be the same thing. And so if one equation has copper 2 and the other has copper metal, automatically it's wrong. I mean, I'd see that right away. This can't be. All 3 have to have copper metal. Okay, what about silver nitrate? Do we ionize that? Yeah, it's a soluble salt. All nitrates are soluble. So what does it ionize to? 2 silvers and 2 nitrates. It has to be balanced, 2 and 2. Copper 2 nitrate, do we ionize that or leave it alone? Ionize it. You know, all nitrate salts are soluble, so we're going to get copper 2 plus 2 nitrates. Silver metal, do I ionize that? No, so we just leave that alone, 2 silver solids. And so the net ionic, we need to get rid of the spectators. Well, we already know what the spectators are because it's a single replacement, so nitrate's got to cancel out there. That as our NIE. And so in other words, the copper metal is being attacked by silver ions. We're going to form copper 2 ions. This is what gives the blue solution. And and then we should get a precipitate of silver metal. Now, the precipitate is not a driving force. Okay, and so that's what's shown here. You can see the precipitate's forming a fur on top of the copper here. And this is just time lapse. This is after several hours. After several weeks, you get a lot more reaction. So you can see the silver build up here. You can see the crystals grow. Do you see the crystals nucleate here? So we're nucleating a whole bunch of crystals there. And then give it time. We could see the crystals grow. Silver likes to form needle-like crystals. There, you can see a crystal of silver there. See that? These are all single crystals, and they branch sometimes too. These are called dendritic crystals. Needle-like structures. Initially, when they nucleate here, they just form a fur because these you have a whole bunch of tiny crystals here. Those tiny crystals then start to grow. So, the point of this slide is concentrated versus dilute. So, I think most people know, like concentrated lemonade versus dilute lemonade. Easily solve the difference there. But since they're doing a redox reaction, I wanted to talk about the redox chemistry happening here. Well, how concentrated can it get? Can it get infinitely concentrated? Well, it depends. You know, a lot of things have a solubility limit, and so there are two ways we look at solubility, and there are two definitions for solubility. One definition comes from the solubility rules. What someone does is they just pick some arbitrary cutoff, you know, and say anything above this line we'll call soluble. Anything below we'll call insoluble. And so solubility has two main definitions. One is qualitative. That is, we have S. S means soluble. We have I, which means insoluble, precipitates, in other words. And then we have SS, which means slightly soluble. And so these are arbitrarily defined. You know, for example, soluble, the way we define it is, what it means is 0.1 moles of solute can dissolve in a liter. And so what we want is we want greater than 0.1 moles of solute to be able to dissolve in a liter. If it's insoluble, then that means less than 0.1 moles of solute. Solute is what we're trying to dissolve in a liter. And so what is that? Well, sodium chloride. A mole of sodium chloride weighs, how much does a mole? 35 plus 23, 50, around 55 grams. And so a mole of sodium chloride weighs 55 grams. Therefore, 0.1 moles weighs 5.5 grams. So can we dissolve 5.5 grams of sodium chloride in a liter? What do you think? Yes? Can you dissolve 5.5? Have you ever tried? It turns out yes. You can dissolve that easily. And since you can dissolve that easily in a liter, then we call it soluble. There are some things that are insoluble, where you can't dissolve it at 0.1 moles. If you can dissolve around 0.1 moles, we'll call it soluble. So slightly soluble means about 0.1 moles of solute can dissolve in a liter. That's qualitative. Quantitative is, well, okay, I can dissolve greater than 0.1 moles in a liter. Well, exactly how much can I dissolve? Can I dissolve an infinite amount of table salt? Let's say I want to make the saltiest water I can. How much salt can I get to dissolve? Well, that's where we want to know the quantitative solubility, or the solubility of sodium chloride. And so that's easy information to find because that's going to be in all tables of data. So if we go to Wikipedia, Wikipedia is a pretty good source for properties, especially these physical properties. Let's go. And we look at NaCl. It's lagging. And sodium chloride, and we look at some of the properties here. We go down the list, and then we see. Well, how much can we dissolve? Well, it turns out we can dissolve 359 grams, and so that's well over 0.1 moles. You know, 1 mole is 55 grams. That's a lot of moles. And so, in other words, this is going to be highly soluble, but what if I tried to dissolve 360 grams in a liter? If I tried to dissolve 360 grams, then I'm not going to be able to do it. I'm going to dissolve 359, and then 1 gram is going to be left undissolved. And so the quantitative, the solubility is defined differently. The solubility is equal to the max amount of solute in a given amount of solution or solvent. Depends, but this could be salt. And so if you try to dissolve 380 grams, forget it. You know, just 359 is the max, and that's what we call the solubility. And so two ways of talking, you know, just because something's soluble, we don't know to what extent. So we said silver nitrate's soluble. Well, is silver nitrate going to have that same solubility? So let's take a look at AgNO3, and then take a look at its solubility here. You know, yes, it is soluble. That means we can dissolve more than 0.1 moles. But it's really soluble. Look at it. In fact, did you know that silver nitrate is more soluble than table salt, or less soluble than table salt? Let's look at it at room temperature. 256 grams will dissolve in 100 milliliters. Is that more soluble or less soluble? Well, it depends. It depends because a mole of water is 55 grams. A mole of silver nitrate is like 140 plus. You know, I mean, silver alone is 107, 108. And then you have the nitrogens, another 14, and then 3 oxygens. So it adds up. And so it depends. If you look at it on a gram basis, then yeah, because on a gram basis, we can dissolve 2,560 grams in a liter. So a liter could be 10 times more. So 2,560 grams in a liter is a lot of silver nitrate, really. But on a mole basis, no, it's not so much because silver ions weigh so much. But anyway, those are just little points, you know. If we want to know exactly how much dissolves, then we consult the solubility in a table, you know, or a handbook, or Wikipedia. Consult it. And so, qualitative and quantitative definitions. take a look. Solubility, measure of how much solute will dissolve in a given amount of solvent at a given temperature. So this is quantitative, exactly. When we have a saturated solution, then we've dissolved the maximum amount. So 359 grams is saturated, or anything more than 359 grams. If we had less than 359 grams, let's say we only had 340 grams, then it's unsaturated because there's still room for more solute. And so we have saturated and unsaturated. We also have something called supersaturated. Supersaturated solution is one in which the concentration of the solute is greater than the normal solubility limit. You know, I just realized something. Did I talk about nucleation and growth of crystals? Have I ever talked about that? Right, what did we talk about that? So when things precipitate, you know, the ions have to come together. But the ions have to come together in an organized fashion so we can form a crystal like that. That's called nucleation. So we form a little baby crystal. Sometimes what helps to form a baby crystal is a seed crystal. So some people put seed crystals in here so that the crystals can grow naturally on top of that seed crystal. So that's nucleate. Crystals won't nucleate here because this is unsaturated. It's not until we saturate or supersaturate crystals. So what a lot of people do is they try to grow big crystals. So they don't want that many sites of nucleation. If you got a lot of little baby crystals nucleating, then you're going to get a lot of crystals. But if you only have, let's say, a few baby crystals, then those few baby crystals can grow to be quite big crystals. So this is all part of the nucleation. So we've nucleated lots and lots of little baby crystals, but we don't have any huge crystals of silver formed here. Sometimes it's hard to nucleate those little crystals. And so this is a case where supersaturation can occur. Supersaturation. Everybody has some experience with supersaturation if you've consumed like a carbonated beverage. If you look at a carbonated beverage here, there's some headspace here with gas. Do you know what the gas in the headspace is? This is pure CO2. CO2 gas. Do you know what pressure it is, roughly? It's pure CO2 at about 1 atmosphere. And so, since there's only one gas there, we can use Dalton's law. The partial pressure of CO2 is going to be 1 atmosphere. It's the total pressure. Do you know what the pressure of CO2 in air is? I'm out of sync with the both classes, so I had it up here. I don't know where it went, so let me just find it again. Air is a mixture of gases. How much CO2 is in air? The composition of dry air, 0.039% carbon dioxide. If it's 0.039, well, we're going to use Dalton's law here. And so that means that if I have 100 atmospheres of air, I would have 0.039 atmospheres of carbon dioxide. So this is 0.039 atmospheres of carbon dioxide per 100 atmospheres of air. What if I have 1 atmosphere of air? If I have 1 atmosphere, how many atmospheres of CO2 do I have? I'm going to have, well, 0.00039 atmospheres of CO2. it's the percent. The mole percent is the same as the volume percent, which is the same as the pressure percentage. So we're getting it using Dalton's here, using it as pressure percentage. So what happens is, when I have pure CO2 here, the pure CO2, the CO2 is forced into the liquid. And so the CO2 gets forced into the liquid. Some of the CO2 escapes, and we set up what's called a dynamic equilibrium, where we have what's called dissolving of CO2 and degassing or dissolution, not dissolution, degassing, or, you know, in other words, we allow some of the CO2 to escape here. Usually escapes by like nucleation of little bubbles. These little bubbles grow. But this is a dynamic equilibrium. That is, having 1 atmosphere of CO2, the CO2 is forcing in. But what happens if you release the lid? If you release the lid, then we go from 1 atmosphere of CO2 to 0.00039 atmospheres. If we go to 0.0039 atmospheres of CO2, is much CO2 present to be before? No. In fact, we had a lot of CO2 to begin with. Now we have none. And so what's happening is the degassing rate stays the same, but the dissolving, or what we call dissolution, dissolving of CO2 really gets cut down because we have so little CO2 out here. And so this is what we call a supersaturated solution. There's way too much CO2 in the water than can be supported by 0.0039 atmospheres. So why doesn't all the CO2 just bubble out immediately when you open the cap? Well, sometimes it does, but most of the time it doesn't. It doesn't because of bubble nucleation. You know, to grow a little baby bubble, everything, all the CO2s have to come together and they have to kind of stick together. And so it doesn't happen easily. And one way to help nucleation of bubbles is to shake it. You shake it, will cause nucleation. But another way is to add something that helps nucleate it, like menthos. I'm sure you've probably seen this, but menthos so we got way too much CO2 present, and so we just need help forming the bubbles. And so menthos can help form the bubbles here. Once the bubbles form, then they can grow. And so there's just way too much CO2 in here. It's super saturated. Let's show a video on this. Mentos and Diet Coke is pretty good. I'm going to have to fast forward this one. Forward back. So open the lid. When you open the lid, then the partial pressure of CO2 goes way down. Actually, they're building some punch. Oh, that's another way that you can nucleate bubbles. Nucleate bubbles like that. Talking here. then let's see if they did this. You could use other things as well. It's supposed to be methyl. All right, so that just shows it would be stable. We call it metastable until you have some nucleation and growth. So that's one. There's another common example of supersaturated solutions. Let me show you. And that would be sodium acetate. Sodium acetate has a hard time nucleating crystals. It's because of the acetate. So sodium acetate. Right, so what's happening here is that we're taking advantage of differences in solubility. So if you heat this up, you can dissolve more sodium acetate. And the solubility of sodium acetate depends on the temperature. So let's take a look at sodium acetate really quick for the solubility. So if you look at the solubility with temperature, it varies. So around room temperature, close to 20, it's around 124 grams. Okay. So we go from room temperature up to about boiling. About boiling, we put 163 grams. So 124 to 163, about 40 grams extra. And so you can dissolve 40 grams more of sodium acetate in water than at room temperature. But what happens is, okay, let's heat it up. We're going to saturate it. So we get about 163 grams in 100 milliliters. And then we cool it down. As we cool it down, the solubility decreases, and we expect the excess crystals to crystallize out. But they have a problem nucleating. Sodium acetate is hard to nucleate because the sodiums have to be in the right position, and the acetates do too. And the acetates are kind of a complex shape. If you take a look at the shape of an acetate anion, structure. There's a crystal of sodium acetate there. There's a crystal of it, and so all the acetates and the sodiums have to be perfectly arranged for this. And so if we take a look at this sodium acetate crystal structure, we can see that it is somewhat complex.
And so basically everything has to line up perfectly. The acetates looks like good too. So they aren't actually bonded, it's just to show the orientation is relative to each other. So everything has to be. And so sometimes things are very sluggish to nucleate because it's hard to get everything perfectly aligned like that. And so what happens is there's a delay between nucleation. And so what we end up with is a supersaturated solution. Sodium acetate is easy to form supersaturated solutions because the crystals have such a hard time nucleating. So we can see it here. In this case, this is supersaturated. We have way too much, and so they put in an object there to help nucleate the crystals. And so once there's a surface for the crystals to start to grow on, then they'll grow like this. The clean glass doesn't provide a good surface for crystal to nucleate and grow. So this was an addition of a seed to help. And so we got way too much sodium acetate in solution, but it just wasn't coming out because we needed some help. Like the Mentos, the seed crystal here does the same job. It just helps nucleate, and then the crystals can grow. Surprisingly, sodium acetate is so soluble it can form these little pillars here. And these pillars are basically this. Here you have supersaturated sodium acetate there, and you can use this as a seed, the petri dish. Put some dust there, whatever, and you get it to come out. So here you can see crystals seeding and then growing there. Otherwise, the crystals don't form. I mean, the crystals want to form, it's just having a hard time nucleating there. If you put a crystal as a seed, here now they have a crystal as a seed, watch how you can easily nucleate now. Oops. It should nucleate so easily that you can grow like this crystal clump top here. So, as it's being poured, then crystals are precipitating out immediately. Super saturated. And then sodium acetate has a huge difference in solubility. You can dissolve a huge amount of sodium acetate in a tiny bit of water, at high temperature. And so there's very little water here, but there is water. And so these crystals were once all dissolved in water. That's what it looks like here. At high temperature. It's not melted. These crystals aren't melted. They're actually just dissolved in water. Another example of supersaturation. Okay, so supersaturated solutions are when there's trouble nucleating new crystals, and therefore it's an unstable situation in which you have higher or greater than normal solubility. Okay, it's not going to last that way forever. Eventually, your soda is going to go flat. It just might take some time, and eventually those crystals will form. It just takes time for it to nucleate. We just sped it up by using seeds. Okay, then there are things that have no solubility limit. There are things that are infinitely soluble. These are called miscible. So miscible substances are infinitely soluble. It's like water. How much water can you dissolve in water? You can dissolve an infinite amount of water in water because it's the same thing, water and water. Is there any limit to how much water you can add to water? There's no limit. But there are some molecules that are so water-like that it's like dissolving water with water, like methanol. Methanol is so similar to water in terms of polarity that you can dissolve an infinite amount of methanol in water. There's no limit, and so we call methanol miscible in water. Ethanol is as well, but propanol is not. Propanol is not. Butanol for sure is not miscible. When we get to like butanol, it becomes immiscible. And miscible means it doesn't dissolve. It's like oil. So butanol and pentanol are already much more oil-like than they are water-like. So those are immiscible. And so here you can see the C crystal being dropped in here into a supersaturated solution. This was the video that you just saw earlier. Here is an immiscible solution and a miscible solution. Immiscible would be like gasoline. How much gasoline can you dissolve in water? None. So you see the gasoline stays down. Over here, this is octane and carbon tetrachloride. Octane and carbon tetrachloride is so similar. It's like, how much octane can you dissolve in octane? As much as you want. If the molecules are very similar, then they should be miscible. Well, these are pretty much miscible, octane and carbon tetrachloride, because they're kind of both non-polar. In other words, we have this thing called light dissolved light. And so how water-like is it? How oil-like is it? It's very oil-like, then gasoline will dissolve in it. It's very water-like at the moment. And that's because the interactions here, for gasoline, the intermolecular forces holding gasoline molecules together are what? What type of intermolecular attractions hold gasoline molecules together? Well, gasoline molecules are pretty much non-polar. You see this carbon and hydrogen. So these are all hydrocarbon molecules. Hydrocarbon molecules are held together by hydrogen bonds. Hydrocarbon molecules are held together by hydrogen bonds. Is that true or false? Hydrocarbons are held together by hydrogen bonds. That's false. Hydrocarbons are held together by dispersion forces. There are these temporary dipole forces, London dispersion forces. And so if we try to dissolve something like octane, carbon tetrachloride and octane, we've got to break apart the dispersion forces, but we form dispersion forces. And so they're very similar in the sense that they both have dispersion forces holding them together. Whereas water, if we try to dissolve gasoline in water, we have to break apart hydrogen bonding. Hydrogen bonding are very strong as far as dipole forces go. And they're hard to break apart because it's temporary dipoles. The water don't make room for the gasoline. There. So we have miscible and immiscible. Miscible is infinitely soluble, and immiscible is insoluble. So when we look at formation of a solution, there are certain things we think about dissolving solutes in water. And so we can look at the details here, but let me skip those and we're going to take a look at this. So sodium chloride, we got to break apart the crystal. We got to break apart the water, and we make room for the ions here. That's called the dissolution process. It's actually, the dissolution process is dynamic equilibrium. So sodium chloride, we can see it here. Actually, this is not the greatest figure for this. But here we have the sodium chloride lattice. This has to be broken apart, and then we've got to break apart the water molecules to make room for these ions. The water molecules will break apart to make room for these ions because these hydrated ions are fairly stable. And these are favorable. And so the waters, what do the waters like? Do the waters like to surround themselves with other waters? Well, it turns out no, they'd rather surround itself with ions like this. And so these have turned out to be quite favorable, favorable, favorable. So the waters, if they have a choice, they'd rather be paired up with an ion versus another water. This is what makes this quite soluble. And so even though the bonds are quite strong here, holding the sodium chloride lattice together, the waters will be successful in breaking apart the crystal. Up to an extent, we can only get to a certain extent, because once we get a lot of ions in solution, the reverse process can happen. The ion can migrate over here and hit the crystal. If it hits the crystal, it gets stick. So the ion comes over here, it sees a positive. Well, it likes the positive more than maybe the partial positive here, so it sticks. And ion bonds. And so this is the dynamic equilibrium process. And The dynamic equilibrium process is that we have dissolving or dissolution of the crystals. And then once we get a larger concentration, those species can come back and stick on the crystal surfaces. And so here we have net dissolving, net dissolving, net dissolving. But if we get a certain concentration of ions or molecules here and they come back and stick, we'll hit a point where the concentration is high enough that the probability of coming back and sticking is equal to the probability of dissolving. So in other words, the dissolution rate, you know how fast this occurs, versus the crystallization rate are the same. If the dissolution and the crystallization rate are the same, then we've saturated the solution. When we've saturated the solution, no more net solution will dissolve. And so this is a state of equilibrium. State of equilibrium means nothing changes. But we call it the dynamic equilibrium because there's always change. The crystals never stop dissolving, and the crystals never stop precipitating or forming or crystallizing. And so, you know, even though the weight of crystals here, the excess crystals, will stay the same, and even though the concentration here never changes, the crystals are continually being cycled. Dissolve, reform, dissolve, reform. So that's our saturated solution, our dynamic equilibrium. So let's go back to this slide just briefly. Yeah. So the basic point of this slide is light dissolves light. That's the first sentence here, the first part. You know, polar likes polar, non-polar likes non-polar. And then ionic crystals, you know, negative ions are attracted by positive region. So this is just showing the water molecules. You know, they're trying to break apart the lattice, the crystal lattice, because of the favorable ion hydration spheres or ion dipole interactions there. You see that. And so once the ions are released, they're surrounded by the water molecules, creating the hydrated ions, the solvation or the hydration sphere. And these are ions that are surrounded by polar water molecules. And this is just showing the dynamic equilibrium. You know, once we get 359 grams of sodium chloride, it's saturated. No more will dissolve, but it's still dissolving and it's still crystallizing. So it's still going back and forth here. This is the dynamic equilibrium. There's zero net change, but there's continual microscopic particulate change here. That's what that slide shows. Okay, factors determining the solubility. There are things that will impact the solubility. One is, you know, how soluble is the substance. And how soluble is the substance depends, like, the strength of the intermolecular forces on all these. It's not just the intermolecular forces, but, you know, the factors that influence the solubility would be like this. You know, some crystals are more soluble, some crystals are less soluble. It depends on how strong the bonds are here. The stronger the bonds holding the crystal together, the less soluble. So if you would go back to the solubility rules, one of the patterns that you see in the solubility rules is that the higher the charge, the less soluble or the more soluble. The higher the charge of the ions, the less soluble or the more soluble. So for example, a chloride versus a phosphate. You know, chloride is -1, phosphate is -3. So the higher the charge, the less, so phosphates are more soluble or less soluble than chlorides. Well, think back. Chlorides, bromides, and iodides are all soluble except for silver, lead, and mercury. Phosphates, carbonates, and chromates are all insoluble except for group 1 and ammonium. And so if we sit there, maybe if we wrote it on paper or looked at it, it turns out that the higher the charge, the less soluble species tend to be. And so this is why something like you know, sodium chloride dissolves here. Another group 1 salts dissolve because they're +1. But like calcium carbonate doesn't dissolve because calcium is +2 and carbonate's -2. It's a much stronger lattice, so it's a lot harder to break apart that lattice, even though the hydrated ions would be better. And then we look at the strength of the interactions holding the water molecules, which is primarily hydrogen bonding. Dispersion are pretty weak. And then we look at the hydrated ions. You know, this is why lithium ions are more stable than potassium ions because of the hydration sphere. Lithium ions are smaller than potassium ions, making them more stable. And so that's the first statement here. The first statement is the strength of the forces. We look at all the forces, the bonds that hold the crystal together, et cetera, et cetera. This could be not just solids dissolving, it could also be liquids dissolving, you know. For liquids, the easiest is light dissolved light. You know, ethylene glycol. Ethylene glycol is antifreeze or coolant. This is highly soluble. In fact, it's miscible in water because ethylene glycol, if you look at an ethylene glycol and compare it to water, do you see how water-like ethylene glycol is? This is ethylene glycol here, this is water here. They're very similar. And so light dissolves light. And so this is like mixing water with water. You know, it's miscible. However, if we try to dissolve oil in water, it doesn't dissolve because oil is not water-like at all. And so breaking the interactions and forming the interactions is unfavorable here. We're just looking at the energetics of this anyway. We aren't going to get into the details, I believe. Here's light dissolved light. Octane and carbon tetrachloride, both nonpolar. Here is unlike thing. Here's light. You know, but you know how water-like are these ions? Well, the ions like this is very polar. Ions are monopoles, they aren't dipoles. These have one charge. Well, this is a positive charge. This is very polar. And so these are very polar. Water is pretty polar. And therefore, light dissolves light. Same thing for gases. You know, water is very polar. So we'll call this water here. It depends on the gas. You have different gases, like O2. Is O2 very polar, or is O2 nonpolar? Is the oxygen-oxygen bond evenly and symmetrically distributed, or is it polarized? You know, maybe the right oxygen is more stronger than the left oxygen. No? And so oxygen is nonpolar. And so oxygen is not very soluble in water, but you can force some. How about CO2? Is CO2 very soluble? CO2 is not very soluble either. CO2 is not very soluble because CO2 is nonpolar. How can you get more CO2 to dissolve in water? You know, well, one way you can make sparkling beverages is by forcing the CO2 into the water. How do you force the CO2? You take it from what's normal. The normal pressure of CO2 in air is like 0.0003 atmospheres. But if you bring that up to 1 atmosphere, you can highly concentrate it. And so what we're doing is we're increasing the pressure of the CO2. If you increase the pressure of the CO2, we can force more CO2 molecules in the water. There are other things that you don't really need to force into the water, things like HCl. HCl is highly soluble. HCl loves water. HCl is polar, water is polar, they like each other. Ammonia. Ammonia is highly soluble in water. Ammonia is polar, water is polar, they like each other. Ammonia. So you don't really have to force it, but if you did force it, you'd get more in. You know, there's a solubility limit. It's not miscible. You can't dissolve an infinite amount of HCl in water because they aren't that similar, but they are alike in the sense that. And so, in other words, this is called Henry's law. If we increase the partial pressure of the gas, we can just force more gas molecules into the liquid phase. And we set up a dynamic equilibrium here, like I was trying to show earlier. Gas molecules dissolving in water and gas molecules evolving out of the water. So you can see there. That dynamic equilibrium. Okay, so pressure has an impact. These are factors influencing. So one overall is the kind of light dissolves light. And then we're going to look at the pressure. You know, the pressure of a gas over a liquid. The higher the pressure of the gas, the more soluble it is. The next thing we look at is temperature. You know. Temperature is going to have different impact on these. So for example, if I increase the temperature, will I get more gas to dissolve or less gas to dissolve? If I increase the temperature, will more gas dissolve or less gas dissolve? You'd think more because, you know, you could force that. But the temperature increases both for the gas and the liquid. And so if the liquid is moving with a lot more kinetic energy, what's going to happen is that's going to force the gas molecules out. And so hot water, you can see this happen because bubbles of gas form in a pot of water well under the boiling point. You know, when you get to about 60 degrees C, you'll see bubbles of gas forming. That's not boiling. What that is that's bubbles of air forming. And so what happens is if you increase the temperature here, you know, little bubbles of air will nucleate in here, well below the boiling point. That's because the solubility of air is going down. It's nitrogen also. So increase the temperature. If you increase the temperature, solubility goes down for gases. But that's different. For liquids and solids, the solubility goes up. If we increase the temperature here, we should be able to dissolve more oil in water because the temperature is going to really break apart the water molecules, allowing the oil molecules to sneak in there. Right? And so if we're looking at liquid and if we're looking at solids, if we increase the temperature here, increasing the temperature here is going to cause more violent collisions with the surface of the crystal, and that's going to result in higher solubility. So solids like this and liquids will have higher solubility at hotter temperatures, whereas gases will have lower solubility at higher temperature.
It does work in reverse. If you lower the temperature,
Yeah.
the gas is more soluble.
Right. In the reverse, it happens that gases become more soluble, and liquids and solids become less soluble. Here's a chart showing it. Now that's just a generalization. Not everything does that. So for example here, cesium, sodium nitrate, cesium chloride, rubidium, all these show dramatic increases in solubility with temperature. As we increase the temperature, we can dissolve a lot more grams in there. Sodium chloride stays kind of flat. Take a look at lithium sulfate. Lithium sulfate actually decreases solubility with temperature. And so lithium sulfate becomes less soluble at a higher temperature. But lithium, we already know, is a little different. Why is lithium a little different than other species like sodium, potassium? Well, maybe in this case, although we have a lithium here, you know, there are other factors that we need to consider with that lithium. And so those could influence why. But there could be other reasons. But the generalization here is, with a few exceptions, solids increase solubility with increasing temperature, especially with something like sodium acetate. Sodium acetate is like 40 extra grams. So sodium acetate would have a curve like this. So at about room temperature, it's here. At high temperature, it's up here. And then you cool it down, it has some trouble crystallizing. So it forms a supersaturated solution. Lithium chloride, not so much. Rubidium chloride, not so much. Cesium chloride, not so much, because those are easier to get the crystals in alignment. You know, that is, the ions in alignment to form the crystal versus acetate. Okay, so those are just general factors. Did you write those down? The temperature, impact of temperature? And the other one is, all you need to know really is light dissolves light and the solubility really. Okay, once we do this, then we want to express the concentration of mixtures. And there are different ways we can express the concentration of mixtures. One way is by percent by mass. We use this for many different things, expressing the composition. But for this, we have different things. We have the mass fraction. The mass fraction is the mass of solute over the mass of solution, or total mass. And so it's mass of component A over the total mass. The total mass would be mass of solution. The solution would consist of the solute plus the solvent. So mass of solute over the total. That's the mass fraction. And then to convert it into percentage, we multiply by 100%. And so that gives us the percent concentration of mass. So when 125 grams of a solution was evaporated to dryness, 42.3 grams of solute was recovered. And so there's 42.3 grams of solute per 125 grams total. What was the percentage concentration of solute by mass in this solution? And so why don't you go ahead and try this calculation here just for a minute. I need to get my charger. I'm about to run out of